is local to local constructions. Well, it so happens that today is completely local, and this local construction will be tomorrow. But so our object of interest in Dima and we want to connect to local definition. Local by definition means that these categories don't feel the global curve. They kind of attach to the form of this. So what happened in the variance law? So he introduced this category with with G or with 0G, X underlying in the one space. So he introduces some category demodels to make the variance condition. And so he also introduced the slope with global contours. That was a very end of the slope. There was a contour coefficient. By the way, this is complete analog of what happened in number theory when you take clear expansion of homogeneous forms. And this contour fits the left adjoint called contour. So it's a good point. Thanks. So this is what happened. This is what happened in the various problem. So now let me put your stop also into perspective. So basically, that was the motivation he was trying to give at the beginning. So our object of interest is global categories with K element geotypes. This category is representations is loop algebra with an integrability condition with respect to L plus D. So at the very beginning, what we're trying to emphasize is that so he took the point of view that central elements in the universal L-big algebra was Katsuri give rise to differential operators of 1G. But this is it's true, and this was kind of the origin of the subject. That's how Deleuze would approach it from the beginning, but that's not the point of view that we actually need now. So we kind of instead of constructing differential operators on 1G, we actually look at it categorically. So we look at the functor of this category. So this is the category that will be introduced, and what will happen tomorrow in Stan's talk. The picture parallel to this is another pair of German contours of local to global nature. This is the contour localization, not to be confused with the spec lockstep, although it's a close cousin. And so there's a contour gang. So this will be tomorrow. Time to go right tomorrow. So now, let me just say also what actually happened with Grubier's talk. So here are the contents. So Grubier defined this category. So it was defined as some kind of Chandra modules. So it's really modules for the Lie algebra with integrability. Well, we call it condition, but in fact, and it's really condition at the level of the Lie categories. At the grad level, it's an extra structure. That's what's emphasized. So that's one thing. So also Grubier explained that this category is self-dual. And so before we talk about self-duality, you have to explain what it means to be self-dual, what it means to be the dual. We will need that, but we will recap this when this notion comes up. So it will actually come up only on day 5. So we'll recap this. So don't worry if you didn't get it. So and now this construction of self-duality was even maybe more important than the fact of self-duality. That used the fact that used this construction of semi-infinite cohomology. So there was a functor semi-infinite cohomology goes from K of G to that. And it's semi-infinite cohomology, if you wish, of LG. But also there was semi-infinite cohomology of loops into N. To that. and also its variant with a character. So we are stated the existence of these functions, and they said that there are kind of variants of cohomology with the following flavor. You kind of take cohomology with respect to L plus and homology with respect to the rest. This is a very imprecise way of saying this, but we'll try to fit the actual definition later in the program. So when we actually need this text. So I think this will first appear in Sam's talk, and we'll try to insert some kind of explanation of how it works. So if you missed, well, some that you missed, details were not given, so you might not be comfortable with using the symbols, but like, yeah, don't worry, we'll still give those reasons. All right, so now, Dima.
Right. So I hope this made sense. On the other hand, my talk will be completely unrelated to all of this because of the nature of the story. This all happens on the one side, and we are kind of going on the other side. So, which means two things. First of all, it's supposed to be quite accessible. So we're kind of going back to basic notions in a way. That's thing one. And thing two is that I'm going to switch to the other side of the geometric Langlands correspondence. So there will be a group G, which secretly should be the Langlands dual of what's going on. And my talk is about the notion of opers. So G opers. And let me also make another general comment. So that just like in this story, we really need to talk about the local story, about the local kind of objects. But historically, I think local and global, no, historical local also here. But anyway, global objects are also important. So I want to spend some time looking at global objects as well. And another basic comment is like, what happens with these opers? I think yesterday somebody said that when we look at connections, it's important for us to think about them as objects on the Deram step of X. Now, that's no longer applies for this talk. I really want to go back to the way of thinking about connections as bundles of local systems, rather, as bundles with connection.
Even that somebody was you.
I know. So we look at G bundles with connection on a curve X. And so G, as before, is going to be a reductive group. And we will also need, as already appeared, it will be important to think about the correspondent Borel subgroup. So I think for this whole talk, it's really good to think about GL3, not GL2, but specifically GL3 as an example. So I'll keep drawing cartoons for GL3. This is my G, and this is my Borel. And so very informally, first of all, an oper is a kind of a bundle with connection, or better said, it's an extra structure on a bundle with connection. Namely, let me say it. So what I want to have is a bundle over the Borel. So oper is going to be FB, B dorsor, B bundle on our curve X plus a connection nabla on the induced G bundle, connection on Fg, which I can write it as G twisted Fb or G times Fb over B, with, so far so good, with an extra condition. The extra condition is, says that this connection doesn't, it absolutely does not respect the B structure. It does not come from a connection on FB, but it, so to say, sits in the next, the discrepancy between these two terms sits in the next term over. And I'll make this precise. So discrepancy, the degree to which nabla disrespects FB is precisely controlled. FB sits in the next term, and it's also non-degenerate. So, I mean, again, this doesn't necessarily have to make sense if you haven't seen this before. The important part is what goes into the data, and I pack this, instead of thinking of it as a B bundle with an extra structure, I think about it as a G bundle with a connection, except that this G bundle also was induced by a certain B bundle. So it's like you have a vector bundle and you have a flag in it. Okay, yes.
Do you mean here a fat connection?
Yes, but I'm on a cure, so I don't really care. It's kind of a fun. And in fact, this notion is specific to one-dimensional. Like there are opers are about ordinary differential operators, not partial differential operators. You need to be in something one dimension. Okay, so now details. Now I want to make it clear what I mean by discrepancy between these two objects and what I mean by discrepancy being in the next term. So first, given my B bundle, by the way, I just realized that probably everybody was denoting bundles by T and then denoting them by F. That shouldn't correspond. So given a B bundle, I can consider the sheaf of locally defined connections on it. So I don't know if, maybe let me underline it just to make it clear that that's a sheaf. And this is going to be, so if you have two connections, they differ by a Higgs field. So this is going to be a torsor over the, like, I guess in general, over the twisted form of B twisted by my bundle and then tensor home. So I can add differential, like basically B-valued differential forms to a connection. Now that I induce, so this is, now that I induced it to a G bundle, I can now ask about connections on this G bar. And this is going to be, again, for the same reason, this is going to be a torsor over the twisted form of G. It doesn't matter whether, I mean, you can either twist by the original bundle or by this induced thing. These things are compatible. Now, which torsor? Well, it's going to be the induced torsor induced under the natural map from B to G. And because of this, we get what I guess we can call a short exact sequence, except these are affine spaces. So, but that probably, I hope it's still clear what it means. So I'm going to have a map. So for an induced bundle, I will have a map from this sheaf of connections to just the sheaf of sections of the quotient. So this is going to be a map from here to G mod B, twisted by my B and like differential form. So this is this discrepancy that I was talking about. So it's going to equal 0 exactly when the connection actually came from when the connection respects our B structure. So in down to earth terms, I'm saying that if I have a differential, keep using yellow color for this, so that if I have a differential operator, this, so I can look at the non-upper triangular part of this. And because I'm looking at the non-upper triangular part, when I look at the non-upper triangular part, all the differential thing gets erased as well. So I just get a section of this vector bundle, no connections, no torsors, nothing like that. Okay. So, and I guess maybe, let me actually maybe add this. I add a picture. And so pictures are always worth spending time on. So I have a curve, I have my curve X, I have the bundle G, and then because I have a bundle G, I can think about the corresponding flag bundle. So the bundle of flags in the flag in my bundle FG, which you can also think of as the flag variety twisted by the corresponding one. So I have so this circle is supposed to look like the variety of flags. Now, a choice of a B structure on my bundle gives me a section. So this is, I should use a different color. This is FB. The choice of a connection, if this is a local system, then this thing has a connection. And you should think of this delta as the derivative of this section with respect to the connection. So if you like, what we're doing here is a calculation of the normal space to this relative tangent space. Okay. Now, that's the explanation of this word. Now, what exactly do I mean by saying that it must lie in the next term over? So now let's just go back to and look at the Lie algebras of GN. So this so the main thing is that inside my Lie algebra G, I have some subalgebras that already appear. I have B, and it's nilpotent, so the Lie algebra of the unipotent radical. So, but I also have the previous term, G minus 1, which formally would be exactly the set of elements in G, which if you commute them with something in N, you go into lambda B. So again, in this story, B is upper triangular and is strictly upper triangular. And this I don't know what to call. Slightly non-split, slightly non-upper triangle. So I'm allowing non-zero entries below the main diagonal. And in fact, if I go down G inverse by B, I'm going to get exactly the sum of all the simple negative root spaces. So this is going to be GL minus alpha, where alpha is. And so in general, the discrepancy has to lie here. But inside this thing, I have this smaller subspace, G minus 1, mod B tensor omega. And this part is very understandable because it splits as a direct sum. This vector bundle splits as a direct sum of line bundles indexed by simple roots. So this is direct sum over alpha of G minus alpha. You should remember that it's not just a constant thing, it's going to be twisted by F of B. And so now I can actually complete the definition. I think it's okay for me to just correct this. So the condition is that delta of this connection, first of all, must be here. So you're going to get a section of this direct sum of line bundles. And secondly, you ask that the section of each individual line bundle is nowhere vanishing. It's a basis. So G B F B tensor omega. This is a subset of that. I'm not going to copy it. And each component in each G minus alpha, the same thing, is a basis, is nowhere vanished. Okay. So does this make sense?
Dima, I think you should remove the quotation marks around definition.
Now, yes. Ta-da. Yes.
We have a fatty or completely.
Sorry.
We have fatty or
The whole point is that this is not, we are, the moment we start talking about bundles, about local systems as bundles with connections, we are firmly settling in the parameter. So, and I think that's the theme of today's day. Things we do today, things we said today cannot be made sense of in the data world, and that's what makes, in some sense, this is. Please, maybe somebody will disagree, but I would say that's why the RAM languages can be easier than better than, because we have these extra tools. Okay. So now,
and maybe just to add one comment to that. If you deal with maybe genus 2, whatever, higher genus surface, then the space of opers on the curve has much smaller dimension than the space of local system. So a generic local system does not at all have an oper structure. But if you have a topological surface, there will exist an algebraic structure on it, so that a generic local. Well, if you have a generic local system for SL2, then there will exist an algebraic structure on your topological surface so that it admits an oper structure.
Right.
So that's just a way of saying it really depends. In the space of opers inside the petty local systems really depends.
Right. So let me, even without dimension, I think we can still say that if the space of local systems kind of depends on the topology only, so technically there is when you deform the complex structure on the curve, the space of local system deforms with it, but the space of opers mapped to it does not stay constant under this deformation. Okay, now I think so. There is actually like what I said here is the original definition of Beilinson and Greenfield, but I have to. I mean, in the situation where G, it works very well for our purposes when G is adjoint, when there's no center, but when there is a center, we want to correct a little bit. So there will be a variation in the middle of this talk. So let me keep this. So, and the variation has to do with the difference between two objects that were already introduced that appeared yesterday, actually. So instead of asking for FB, so make FB a point of 1 and omega. Now, I don't know if you remember what that means, but really this means that I want, but let me remind you, this means that I want a B bundle, but I'm fixing its reduction to T, and this reduction to T is somehow normalized using omega. So a bond B cross over bond T with a specific point that I think because I passed to the dual group, I have to now denote row check of omega. So I mean, the difference, this extra detail is not super important. I mean, it's a detail, but let me say what I'm trying to say in the case of SL3. So let's continue this example because it's SL3. I'm using yellow again. So I have so we're talking about rank 3 local systems. So E is a rank 3 local system, and the first definition talked about flags in this local system that has to kind of be slightly disagree, slightly transversal to the connection. So we still have that. We still have in our E a flag of vector bundles, not of local systems, of ranks 0, 1, 2, and 3. Now, this condition says that I ask for the respective quotients to be powers of omega. In general, they will be powers of square root of omega. So as Dennis said also yesterday, square root of omega actually has to be fixed for a lot of these things. So, but yeah, for SL3, I will just say that this quotient has to be omega inverse. This quotient is going to be O, and this quotient is going to be omega. So, and now the condition on the discrepancy says that
I think you're up 1 minus 1 state flip.
1 minus 1.
yes, close enough. So so I have this, yeah, of course. So now I have my connection, which is just an operator satisfying the Leibniz condition, and this part is going to ask that nabla of EI, so that the connection sends EI to EI plus 1 tensor omega. Now, once you have such a thing, it's going to induce that nabla induces a map from EI mod EI minus 1 from the associated grade. You're going to get a map you're going to get this map. And before we passed to this variation, the best we could do was ask for this map, which is just a linear map, to be nowhere vanishing. But now that these quotients are somehow pinned, this, I mean, in this case, this is literally, these two things literally going to differ by omega. And so I can ask for this map not just to be some isomorphism, but to be the isomorphism compatible with this data. So this is not just non-zero, but the given isomorphism coming from this pin. And so I explained what happens for SL3, and in general, it's you can make the same definition in general. Okay.
I have a question.
Yes.
Literally the thing you wrote there, like, I think you can write like E plus like 1 star the way you wrote.
I'm about to, yes.
Okay.
So I'm not like I'm almost done with this line, except I can make some parting remarks. So, like, first, so what basically happened? So very informally, we are looking at connections. So oper is some kind of globalization of the idea of a connection of the form d dt plus 1 1 1 1 0 and that block d. And you can even see the difference between the two definitions, whether we ask for this under diagonal terms to be non-zeros or ask for them specifically to be one. And the idea is that that's basically the connection version of rational normal form or companion matrix, however you want to think about it. So we consider this, and in fact, you can even make this analogy stronger, like we consider these things up to, so to say, triagonal base changes. And so if you want, you can, for example, you can make certain entries 0 in this. So you can make this like look like an actual canonical form. I'm not writing this down because I'll write this down in a couple of minutes anyway. So this is, let me just call it rational canonical form for connections. However, because we are working globally, not everything is going to be in canonical form. So the picture you should have is that this is the stack of local systems and the space of, and again, as Sam said, if genus is high enough, and I guess G is semi-simple, then this stack of the opers just embed into local systems as something of dimension half of this. So okay, that's point 1. And then point 2, which again we'll see in examples in a moment, I want to just leave it as a slogan that opers are two connections as nth order differential operators are to systems of n differential equations of first order. These are nth order ODEs to systems of n first order ODEs. Okay, I'm happy to leave it triptych in this form. Unless there are questions. Yes.
What do you when it says like when it's not just non-zero but the given as well?
I want to say that this data, the fact in this variation, I'm now asking more from SB. I'm asking it not to be just an arbitrary B structure, but a B structure together with a isomorphism between the induced T bundle and this. And so in the case of GL3, I'm asking not just for a flag, but for a flag together with this extra pieces of data. And fixing these extra pieces of data provides an isomorphism between the source and the target of this discrepancy map. And I'm asking for the discrepancy of this connection to be that isomorphism.
Can I just add one comment about this? It's confusing just to orient people if they will try to read anything about this. So the notion of opera was defined by Valenson and Grunfeld, and they wrote the definition that's above. Unfortunately, this definition is only really correct as is for adjoint groups, correct in some philosophical sense. So a slight modification of this definition, the variation thing you're saying here was given by Dennis and Glenn. And the variation one is the thing that we'll be talking about for the rest of the week. It's the thing that has kind of nice functoriality in a geometric language. It's the thing that does X, Y, Z things that you just say you want. The two things canonically coincide for adjoint groups. So if you think about adjoint groups a little bit, you'll see that this definition gives you a reduction, a third line to this finite omega. But in general, it kind of only does that on the adjoint group. Dima is saying you should lift because or something. And that's just a thing to be aware of if you're looking at this. So this is it's a small thing, but it's a point of view. It's just better to fix the reduction and if you think these opers, like Dima was saying, there's supposed to be some globalization of the costant slice with ODEs fit into them. And if you think there's kind of two definitions of the costant slice, one that's kind of right and one that's kind of wrong, when they coincide for adjoint groups, and it's exactly this sort of flavor.
So I guess I can only add to this that when we talk about valence on Greenfield, the text is called quantization of the Hitchin vibration and the level.
Also another definition.
I want to think about it as the version of this definition, but really for the purposes of this, as Sam was saying, for the purposes of this conference, the variation, you can forget about that. Just consider add the extra conditions, add this extra piece of data, and the corresponding extra condition.
Question.
Yes.
So in this example, it's a E with that filtration isn't the data of FB.
Sorry, the filtration, I mean, like, what is FG in this example, right? FG is by definition automorphisms of the vector bundle. And then FB would be automorphisms that preserve the filtration. So like, once you change coordinates, you're saying that upper triangular matrices are matrices preserving a flat. Yes.
So the space of opers and bets as a thing of half poetry.
Yes.
What's the
I mean, it's Lagrangian and the symplectic structure of process. So, okay, now we're going to leave this. This is the global story. We're going to leave and go to the local story. So, informally, I can again add some kind of general diagram relating various pieces of the theory. So, global opers, what I was defining here, have to do with quantization of the Hitchin vibration, but this means they have to do with d modules on bar G, while local opers That's evil. Yes. Local opers have to do with the representation of the Cas Mundial. So that's local opers is the tie between what happened earlier today and what's happening now. Perhaps if I just say Cas Mundi, I don't have to put teacher in. So, but it is there. And so, and ideally, so in an ideally, and for the purposes of the proof, it's necessary to when we say local, local should be understood in the sense of the run space. So we should consider arbitrary finite subsets of our curve as they fuse and run around. Ideally, in the run space, in this talk right now, I'll just look at a single point. Single. And I want to say that I don't know, like, I think now is a good moment for reflection. Like, when you see this, does it make you happy or does it make you tense? And I want to say that really it should make you happy, because when we go to the disk, some things become harder, but at least in the beginning, things become simpler because you don't have to worry about things like no trivial G bundles. On a disk, basically everything, you can just write everything in coordinates very explicitly. If the answer comes out to be complicated, okay, that's fine. So we will be, so the point is fixed. There's a disk around this point, which always means this conference, of course, always means the formal disk. And so, and the following spaces will be important. So there will be several versions. In fact, let me erase the line as well. There will be several versions of the oper spaces. Several spaces. One is what would be called the space of regular opers. I guess I will maybe. So dx stands for the disk. I don't know if to draw the curve as something one-dimensional, two-dimensional. So anyway, dx is the disk, formal disk around our point, so formal neighborhood. So the first space will be the space of regular opers on the disk, and let me immediately go to examples. So really, this means that I consider again this kind of differential. Too many zeros. This kind of differential operators. And now let me actually, I'm trying to understand the geometry of this space. And in order to understand the geometry of this space, I want to further make some base changes to make this as simple as possible. And the claim here, which really goes back to I erased it. The Beilinson and Drimfeld's text. The claim here is that you can basically use the rational normal form. I think for some, for the purposes of this example, I would rather use the upper row instead of the upper column, instead of the leftmost column, rightmost. That's hopefully that's the most serious mistake in this talk. So I will have.
I think there's another serious mistake, which is that it's due not to balance in Drimfeld, but Drimfeld so collapse.
Okay, you're right. That's a 50% mistake. Okay. Right. So So for GL3, I'm just going to consider differential equations of this sort. And because I work on the formal disk, now A1, A2, and A3 are going to be formal powers. Now, the reason I wrote it using this slightly strange way is so that when you write it as a when you write this system, the corresponding system of ordinary differential equations, it will literally be equivalent to a single ordinary differential equation with these coefficients. Now, if let me write it, I'll probably mess up pluses and minuses. So this, I can write it in this form, or actually, or even better, even better. So write it as, let me just put plus and minus, or A1x d2 minus 2 minus A 2x dx. So I'm just saying that system of differential equations corresponding to this matrix correspond to a single ordinary differential equation. Yes. Okay. So, and what this means is that so one way or another, when I look at this things, I see three Taylor series, and each of them has infinitely many coefficients. So I have infinity times three coefficients, but there are no real relations between this. And so the claim is that this space is really just an infinite dimensional, it's a scheme, and as a scheme, it's in fact an infinite dimensional affine space. So the space is a infinity, and this is a scheme, the spectrum of the polynomial ring of infinite many. And let me also maybe very much in passing, let me say that, of course, I gave you an example of how this works for GL3, but you can also make this work for arbitrary group. The key is to think about the centralizer of the regular network. So extends to G, and the hint is consider the centralizer of F. Okay, so that's our first theorem, and again, geometry is not super common. So the next object enters the play is this space, where mer stands for meromorphic, which really means that I'm now, instead of looking at opers on the disk, I'm going to look at opers on the functions. So opers on the function is okay. That's more complicated somewhere, but on the other hand, purely formally, the same description applies. The only difference is that the coefficients now, instead of being Taylor series, will be Lorentz series. So absolutely the same thing, except now AI are going to be Lorentz series. And what does it mean? What's this Lorentz series? So this means that we can first fix the order of pole. So, and consider x to the power minus n times c of x, and then take the union of all of this as n let me write it like this. Union as n goes to infinity. The point I'm trying to make here is that this space of opers naturally appears as a union of the space of meromorphic opers, naturally appear as union of opers with a fixed order of pole. For each fixed order of pole, you only get this, but as you take the union, you get this is no longer a scheme, this is an int scheme. You have a collection of infinite dimensional spaces embedded via closed maps. So this is an int scheme. Let me keep running it as a union of meromorphic opers of order at most n, and each of those individually, however, is understandable.
There's no stacky.
No, and that was part of the it's still on the board. Part of what we gained from finite things. Like where if we in the original definition you would still get some automorphisms of all. This one.
And just to add to a comment for the expression, so this already happens just with the finite dimensional ghost and slice, which really shows you like 99% of the phenomena of the subject. So if you take your Beer's formula f plus b naught n, well, Ghost's formula, then that's you take that as a stat, but the fact is it's an affine scheme. In fact, it's just an affine space. It's not a stat. You only do the stat portion. And it's same phenomenon that's happening here. So this is some version kind of maps from the curve into the ghost and slice, but twisted by some one form, it's deformed by some connections. But it survives twist processes.
Okay. And so now finally our last and maybe most important for this last layer is actually is a subspace of this called the space of monodromy-free opers. I mean, free is do, right? So free X. So these are monodromy-free. And in other words, the definition is that our oper, that the underlying local system, instead of just being a local system on the puncture disk, should be a local system on the entire disk. So if we were in the classical situation, if we were in the if instead of a formal disk we had an actual disk, we would just say that monodromy around the puncture should be 0, 1. And so let me write this formally, that we just define this space to be the fiber product. So we have our meromorphic opers, and we ask for the local system on the puncture disk to be lifted to the local system on the entire disk. So this is the at 0 in addition to the puncture disk. Okay. So now that's a non-trivial condition, because we first write this, like, let's see what happens for SL3 or GL3. So we write this kind of thing where these coefficients are now Laurent series, so they're allowed to have a pole. And now it could happen, despite the fact that in this basis our connection has a pole, it could happen that after a change of basis, after a gauge transformation, if you use old-fashioned language, classical language. So if you can remove the pole. So, or if we use a language of ordinary differential equation, I ask for a differential equation with Laurent series as coefficients that has a fundamental system of solutions which are also Laurent series. Nothing more complicated. So this A1 of x blah blah blah. I guess I didn't say much here, such that there are three linearly independent, well, three is n, so independent solutions. So- okay, and so now this geometry, now the geometry is going to be more complicated, but it turns out, and I think I'll have to leave this as exercises, but trust me, I mean, they are not immediate, but they are also not, there are no real tricks there. So let me say some geometric properties of this. Now, first of all, I guess,
Are you gonna show us your GM at some point?
I mean, do you want to see? Depends on what you want to see. Dennis is not here. So I'm also, I have 2 minutes left. Oh, you are here. Okay, but don't do this. So would you rather see an example or would you rather see the definition of incoherent sheet? Sorry, you overruled. So, but yeah, let me say, so I will still run over, but hopefully in a controllable, it will be a controlled crash. Okay, so let me say what the geometry of this thing be. So first of all, it's formally smooth. And in fact, you can try to write it as a union. So you can write it as a union of, in a similar way, write it as a union of closed subspaces, subschemes actually.
Who's following this move? The one?
I'm talking about this guy. Yes, so this is a union of closed subschemes, and each closed subscheme can be written as a product of something finite of finite type, so something finite dimensional, and an infinite dimensional affine space. So technically, it's still this infinite dimensional, but this infinite dimensional structure is very simple. It's like it comes with no restriction. Okay. And so all right, and so we come to the last point, namely,
Both subspaces are spaces.
sorry, I didn't hear the question.
Are these both subspaces are spaces of some finite vector?
I don't think so. Not by construction, at least. No, but I mean, it's true that this is what you get when you look at arc spaces, right? So you have this, but yeah, I don't think they literally are that.
Is present open inside Monodromy-free or not?
Right, I know.
Is the first one inside the third one?
Yes. So regular sits inside here, this sits inside here. But the problem is that this one is kind of more complicated, but we can still say enough about it. And so now the last question, what kind of sheaves, by which I mean something like quasi-coherent, incoherent, I will say coherent, so that leave or on this kind of objects, on such spaces, where really by such I mean something like finite type times y times n. And I mean, there is more than one answer. You can make sense of so you can formally define different things. So the question I'm going to answer is really what kind of sheaves living on these spaces are relevant to our story. So we need something that technically would be denoted in core star. And what this is in this situation is actually very easy to explain. So this int core star of, let me just forget, let's not forget about y for a moment. So the point is that this scheme naturally appears as naturally comes with projections onto finite dimensional quotients, really. And the natural, so maybe I didn't make clear what problem we're trying to solve. So the core issue here is that we're trying to deal with coherent sheaves on something of infinite type. And we want to formulate the right object. And so the right object, the right answer says that finitely generated sheaves over a ring of infinite type should somehow come from from subrings of finite type. So this is what those quotients are about. And the subtlety is in making sense precisely of the word come from. And there are two versions to do it corresponding to star and shape. And so let me write the one we consider here. So I'm going to write, this is going to be the co-limit of, I'll just write it like this, in co of y times an. And the point is that if I project and I project further, there will be a connecting map. And this connecting map, the pullback for this connecting map will send coherent sheaves here to coherent sheaves here. So here I'm looking at the pullback. So because I'm looking at the specifics of the situation, and so I can have this pullback, and I'm going to use the star pullback. If you work with coherent sheaves, you may know that there is also another option. I don't care. I'm using the star pullback. So the limit is taken under star pullbacks, which really is just, I mean, you're just saying if I have a module over a ring, over a smaller ring, I induce a module over a larger ring, and then if I want, I can. So if you were really after understanding coherent sheaves on this in the most obvious way, this is the definition. This is the closest counterpart of this definition. So this thing will be compactly generated by actual coherent sheaves on this thing. Yes.
And why don't you just upper star of the because these are the guys which we want to take global sections. They're exactly the things, and that is the case of the
Let me actually modify this answer a little bit. So the point is that when you live in the infinite dimensional case, you cannot have O and omega at the same time. You have to choose, because normally O and omega differ by cohomological shape by dimension, and now dimension is infinite. So there are two versions of this category. One has O and the other has omega. This is the one with O. This is the naive version of coherent sheaves, and that's the one we want if we want to talk about sections. Sections are homes from O, so we need O. So that's our category, and well, I guess we can then extend it to int schemes by taking pullback by taking the starting. Shape fine. Yes. Yes.
A little specific to the situations, is it like all sections on y times a infinity of coherent rings each would have just said code and then left it at that?
I mean, the point is that this definition makes sense, so it's better to give this. So I sort of already twisted the definition, and I was allowed to do this exactly because I fixed a point. So if you don't fix a point, you have to be more careful. So it's better to. So I'm kind of. I would say, yeah, in this specific example, I completely agree. We just have in of core of that.
Which is also the same as in the perf because it's a regular array.
No, why? No.
Yeah, well,
Why?
right. I mean, it's formally smooth, but I don't know that I can choose y to be smooth, right?
Okay, sorry, yeah, I was thinking of.
Yeah, so for this one, you have to be careful. But yeah, it's like int core of y times quasi core of a int perf or anything reason.
Let's just say monotypes, and then from the union, you take the red unit of leaf under control.
Yes. That's it.